let's use what we know about the logistic equation to examine the dynamics of a population. Just for an example, to have some concrete numbers to hand, let's use a growth rate of 0.1, and let's suppose that the carrying capacity of the environment is 500. So that means 500 is going to be our K value, and 0.1 will be R. So if we write down a logistic equation for this situation, we're going to get dp dt equals our growth rate, 0.1, times P, times 1 minus P over the carrying capacity, 500. So the sorts of questions that I want to ask are things like figuring out what is the long-term value of the population, what population size has the largest growth rate, right? So we know that some population sizes don't grow at all, some shrink, but some population sizes will cause the population to grow, so that makes you wonder which one has the largest growth rate. And also let's look at some graphs of possible solutions or possible population functions given this starting point, or this logistic equation. Now, for some of these questions, we don't actually need to solve this system, right? So for the long-term value of the population, we don't need to solve the differential equation because we know the phase line for this equation, right? The phase line for this equation looks like this. We already worked this out. And this lower equilibrium is at 0. This upper equilibrium is at K. And negative values of population are unrealistic. So we won't even consider what happens down there. All right, well, you can see that if our population starts at anywhere except 0, say here, the phase portrait or the phase line says it's going to move towards K, right? If we start here, the population moves towards K. If we start up here, the population moves towards K. So no matter where we start, except at 0, the population will always move towards the carrying capacity, K. So one possible long-term value of the population is the carrying capacity, which is 500. Of course, if you start with 0 individuals, you're going to stay at 0 individuals because, the individuals aren't going to appear from nowhere. So the other possible long-term value for population is 0. So those are the only two possibilities. All right, so what about the second question? What population size gives us the largest growth rate? Well, right, this differential equation, it gives us a way of looking at this growth rate as a function of population. This is a quadratic. It's opening down because the leading coefficient is negative. And right, we know that the horizontal intercepts are at 0 and at K because that's where we have equilibria. So what we want to know is where is the largest growth rate? Well, remember, in this picture, the vertical axis is the growth rate. So we just want to know where this graph gets as high as it ever gets. Since this is quadratic, there are a couple ways of doing that. We could either just take the average of the two x-intercepts, right, or horizontal intercepts. On a quadratic, the vertex is always halfway between the intercepts. But maybe a more calculus-y way to do it is to find population values where this slope here is 0. So what we could do is take this function, 0.1, I'm going to multiply it out, so 0.1 divided by 500 times p squared, we need a minus sign, plus 0.1 p. If we differentiate this and set it equal to 0, we will find p-values where this tangent line is horizontal, and that will be a maximum. So if we differentiate, we get, let's see, minus 0.1 over 250, I guess, times p plus 0.1. Now we're going to set this equal to 0. So now we can multiply both sides by 10 to get rid of the 0.1, I guess. So 0 equals minus 1 over 250 p plus 1. Move the 1 over. 1 is minus 1 over 250p. Oh, sorry, minus 1 here. And then multiply both sides by minus 250. So we get positive 250 equals p. Right? And our carrying capacity was 500, so sure enough, halfway between 0 and 500 is this population value that gives us the largest growth rate. So just with this differential equation, without actually solving it, we can find where the equilibrium solutions are, where solutions increase, where solutions decrease, and where the rate of largest growth is. Okay, to answer this last question, graphs for the solutions to this, we are going to actually have to solve this. But remember, we worked out a general solution to the logistic equation. And the general solution was the population is, there are a couple different ways to write it. One way is it's the carrying capacity over 1 plus some constant times e to the minus rt. Or another way to write it, right here, this constant is not the initial population, but it's somehow related to the initial population. Another way to write it was k over 1 plus k over the initial population minus 1 times e to the minus rt. So this way of writing it, right, this stuff in parentheses, that's c. But this way of writing it makes it explicit what the it makes it explicit how the initial population shows up in the solution for the entire differential equation. Okay, so for us, remember k was 500 over 1 plus 500 over initial population minus 1 times e to the minus. Remember, r was it 0.1 or 0.2? I forgot. 0.1. 0.1 t. So let's put this into GeoGebra. Now, one nice way to do things in GeoGebra is we know we're going to have some sort of initial population. So let me put a point here. I'm going to put it on the vertical axis, which is representing population. And what we'll do is we'll use the vertical coordinate of this point as the initial value. So I'll show you how to do that. We are going to want to have our carrying capacity showing up on our graph. So let me shrink the axis here. Okay, so we need to define this constant c. And c is, first of all, I guess, k is 500. This constant c is k over the initial population, but remember the initial population was the x-coordinate of this point. On GeoGebra, you can get the x-coordinate of a point by using this x function. So x of the point A, like that. Since this point is A, it's labeled up here. So that quotient, k over the x-coordinate of A, minus 1. Okay, so that gives us our c value, which shouldn't be infinity. Oh yes, I made a mistake. We don't want the x-coordinate of that point. We want the y-coordinate of that point. There we go. And now we can graph our solution functions. So I'll use x instead of t just to make GeoGebra happy. GeoGebra likes it if your independent variable is called x. So the function is 500 divided by 1 plus c times e to the negative 0.1 times independent variable. And there we go. So you can see that this solution is approaching our carrying capacity. If we shrink the initial value, the way that we have it set up, GeoGebra will automatically recompute c, and then it will adjust the definition of the population function to match. So as we move this initial value around, the solution that we are graphing should follow it. So for very small values of p, right, it takes quite a while for the population to for population growth to kind of get going. But once it does get going, sure enough, it grows towards the carrying capacity of 500 and then levels off. If the population starts out very close to the carrying capacity, well, then it doesn't have much room to grow, so it just grows very slowly. Although, if you look back into the past, you can see that, well, it grows slowly now, but in the past it grew more quickly when the population was smaller. That makes sense. One interesting thing to note about all these solutions is that all of these solutions, they're the same. They're just moved horizontally. If you sort of ignore where this black point is, as I move between these different solutions, these are all the same graph, but just sort of translated horizontally. If we set our initial value to exactly the carrying capacity, then we just get the constant solution at the carrying capacity, right? And that's no surprise because we already knew that 500 was an equilibrium solution. If the initial population is bigger than the carrying capacity, right, we find that, sure enough, the population decreases towards the carrying capacity. And if we rewind time, we find that in the past, the population has to have been very, very large for it to only now, at the initial time, being this close to the carrying capacity. So the point here is that if you start above the carrying capacity, even if you're very, very far above the carrying capacity, the population rapidly sort of dies off towards the carrying capacity. Of course, when I say rapidly, it depends on what the growth rate is, right? The smaller the growth rate, the slower this will happen. But compared to how slowly population growth can happen if you're below the carrying capacity, the die-off from starting above the carrying capacity is quite quick. I guess one last thing we could do here is look at what happens if we change the growth rate. So let me get a growth rate, so 0.01 to begin with. And let me redefine this population function so that our growth rate is in here. So instead of 0.01, I'm going to write r. And let me get a slider for r. So now we have a growth rate that we can adjust just by moving this slider around. So if the growth rate is bigger, then the population will grow faster, which makes perfect sense. So now instead of sort of lazily approaching the carrying capacity, it actually barrels towards the carrying capacity very quickly. And if the population starts above the carrying capacity, it dies off towards the carrying capacity very, very quickly. If the growth rate is smaller, in fact, this slider is stepping from 0.1 directly to 0. Let me adjust this slider, I guess. Let's say the minimum is 0 and the maximum is 1 and the step size is 100th maybe, or 1,000th. Here we go. Okay, so if we decrease this growth rate towards 0, you can see that we do still get that same sort of S shape. Far to the left it's close to 0, and then the population growth gets going a little faster, and then as you approach the carrying capacity, the population growth slows down. But the smaller this growth rate, the longer this thing takes to get up towards the carrying capacity. And that makes perfect sense. That means that calling R a growth rate is a good name. Of course, if we make the initial value larger than the carrying capacity, we still get this die-off, but it's going to happen more slowly because the carrying capacity is lower. Or I'm sorry, the growth rate is lower. In fact, the different graphs we're getting by varying the growth rate, right? If we just compress the horizontal axis, right, you can see that these are all the same shape. It's just that the horizontal axes sort of have different scales for different values of the growth rate. So in some contexts, people will normalize the growth rate and just set it equal to 1. But then you have to adjust your time units to match.